Recently we've made an experiment with one of the students who is also here. We tried to feed data, the spectroscopic data, for one of the highly inclined spiral, well, early type spiral, which early or late type, it's not actually the point, but the point is that we try to feed the spectrum and to feed two separate kinematical components inside it, in order to separate bulging disk from the spectrum, not from the photometry. Because you can feed the two component LSVD, specifying two different stellar populations inside the model. And then we actually see that what you measure when you plot the rotation curve along the major axis, it's not the disk rotation, because in the central part it's disk plus bulge. But when you separate the two subcomponents, one with low velocity dispersion and another one with a high velocity dispersion, you see quite well that the bulge does rotate. Maybe well, of course, it's slower than the disk, but the disk itself is actually much stronger than what you see when you measure the integrated kinematical profile. Unfortunately, we didn't make the structural decomposition, the photometric decomposition, because we haven't had time yet. We're working on this. But anyway, it would be interesting to try to apply a similar technique to your data, because we're using the spectral fitting, but not one as you are using, but slightly different way. We also fit stellar populations.
So these are spectra taking along the plane of the disk.
Yeah, we have one galaxy which was taken with a 6-meter telescope by Anatoly in his observing program, and there is major axis and minor axis. And along major axis we can quite well separate bulge from disk from the spectrum kinematically.
It is almost face on.
It's not, it's no way face on. It's 45 or 50 degrees inclination. So it's quite,
okay,
and you see
330. But, so when you fit the minor axis spectrum, can you see two components again?
Well, for the minor axis we can see not only two components but also the dust effect, and you can see it even in the stellar population profile, because actually part of the bulge is above the plane of the disk with the dust, and another part is below. And so the part which is above, it's actually dominated by the bulge. So you see the population zone. In the other one, but you know, when you separate them, you see immediately the fraction, the difference.
But you can still separate two components in the minor axis spectrum.
We can separate the two components in the minor axis by the stellar population, because we fit different stellar populations, not only two different chemicals. We can discuss it during the break.
You can discuss it later. Questions?
The enhancements we find at the ends of the peanut structure, as well as those that you have closer to the equatorial plane, that we question as a spiral arms made, etc. And this has to do, one can understand it by means of the backbone of periodic orbits that build this structure. So the family of periodic orbits, as the energy increases, and as, let's say, in the RZ plane, R increase in both R and Z until a certain energy. At the certain energy that corresponds to a certain R, then they increase practically only in Z. So in the RZ projections, there at the ends we have overlapping in the orbits, and then this causes the enhancements at the end of the peanut. And apparently also the other two black holes that we had on the sides were also the same phenomenon for the next family, since the peanut is part of the bar. Then with another family, dimensions of the next part of the bar, the larger distances, and then you get also these enhancements.
You mean this one?
No, even the other one. The one that we had also the questions of this okay. This, but also the enhancements at the end of the...
Okay, this is the peanut for sure.
This is the peanut, so this is what I exactly described. And also I think that those other two, as you say, if there are spiral arms, can be the same thing for another family that does not reach the Z distances from the plane that the families of the peanuts reach.
Right.
Yeah,
well, I think in this case here, I would say this is not part of the backbone of the bar, right? Because you can see that it's slightly curved. It really looks like something in the disc.
So at the end, you see, especially the right ones, it's almost black. It's not the only case. There are many others.
But maybe this case maybe could be the. But yeah, and then this structure here. But are you saying that this structure here could be part of the bar?
It's difficult to say from an image. The mechanism is there, and the previous image was much more clear. The peanut is part of the bar.
The peanut, yes.
So you have to get something else to be correct for the bar. And practice the same mechanism of the different functions that are lower in Z.
Somehow here in rotation curves.
No, in this work, there's no. We just try to avoid dust as much as we could in the positioning of this plate.
Because if the KS images edge on, you have about 190.
Yeah, I mean this is a KS image, right? And then this is the you can still see a lot of dust in the residual image, right? But what I did for the image decomposition of these galaxies, when there are cases like in this case, was to mask the regions affected by dust out of the fit. Because if you fit without masking the dust,
So
the fit is not good.
You can mask them.
Yeah.
You can do them.
No, it doesn't. It's not done automatically. You have to do this by hand.
Many more classical bodies than pseudo bodies. Did you expect that, or would you say that this implies there are more classical bodies than not?
No. This is a sample taken by hand, right? It's not complete in any sense. It's just some interesting cases to study. So the difference between the fraction of classical and pseudo bodies here, I wouldn't draw conclusions. In fact, the other work I showed with the slower images, this was a volume limited sample, and then we could draw conclusions. And if I remember well, it's like about a third of the bulges are pseudo bulges. You can see in this plot. So you see all the pseudo bulges on the dots. There's about the it's about a third.